Hello, welcome to our next set of stats notes. We are on section 9.1, starting our last unit. So these notes we're covering from here until the end of the semester, or what we're going to have our last exam on. What you'll see over the rest of this semester is we're going to do a lot more hypothesis tests and confidence intervals, but we're going to do them for specific situations. So each section will cover a certain situation, and you'll see kind of the different variances and stuff. There'll be a few things that are not hypothesis tests and confidence intervals, but the majority of what we do will be those. So we'll do those a lot. And a lot of these you'll see have nice ways to do these with a calculator. So we'll really rely on the technology of the calculator for most of these. Okay, so 9.1, we're dealing with two populations, and we'll be looking at proportions. So the big difference here is in the chapter 8 and chapter 7, we were dealing with confidence intervals and hypothesis tests. We only had one set of data. We were just looking at one population, one group, and building a confidence interval or hypothesis test from that. In this section, we're dealing with what if you have two populations and you're trying to compare them. So this is the test you would use if you're trying to show that the people in South Dakota are more likely to have health insurance than the people in North Dakota. And so you're looking at the percentages of one state versus the other. Or if you want to say that the incomes are the same, if you're comparing the two populations. So we're looking at just a single population, but now we're going to look at samples from two populations and compare those. So we're going to use this notation down here. So we'll have population 1, we'll have the population proportion, will just P1 versus just P when we only have one population. Sample size will be N1 versus just N normally. Number of successes would be X1, so that's the number of people that have the trait we're looking for or things that have the trait. Sample proportion, so P hat 1. And failure proportion, Q hat 1. Of course, all those things will be the same for population 2. They'll just have a 2 instead. So this is the notation we'll be using. Again, there's going to be the 1s versus the 2s. So we have two different populations. So first off, let's start with our hypothesis tests. Like we've seen before, when we do hypothesis tests, we're going to have some kind of claim of equality, and that's what we'll do here as well. And then we'll take our claims and we'll test them. This can be used for lots of different things. We have two populations, things like the percent of crimes, the percent of people with the health insurance, percent of people own a home. Anytime we're looking at like the percents of the two populations, trying to compare them. When we're doing these, we do have those standard requirements that things are simple random samples, which you won't really have to worry about. I'm not going to give you ones that aren't. But if you were a statistician developing a study, you'd have to make sure you had that. Samples must be independent. They should not be related or naturally paired. So you're only using this when there's no like actual connection between the two people. So I'm not going to be comparing like spouses or siblings or something like that where there's natural comparison. I'm just going to be picking a random group from one group and a random group from another group, and they're going to be independent, not connected. And then the sample should be large enough. Remember that we want both the number of successes and failures to be bigger than 5. So if you have less than 5 successes or failures, you can't do it. That's typically the one thing we saw kind of throwing this. I don't think I actually have examples in this section because we've kind of seen that before, so we're not going to worry about too much. But that's something you always look for. If your samples are too small, you might not have enough successes or failures. Okay. Like always, the null hypothesis is going to be a statement of equality. So for these, the null hypothesis is that the two populations are the same. The proportions from the two populations match. So the percentage of people that committed violent crimes in this state is going to be the same as the percentage of people that committed violent crimes in that state. 2% are matching. The alternative hypothesis, the other options, are either going to be not equal to, less than, or greater than. So either they're just not the same. Population 1 has less violent crime than population 2, or population 1 has more violent crime. Those would be like your 3 different alternative options. Now to do these hypothesis tests, we will need test statistics so that we can either calculate the p-value or check the critical values. So either method, you have to have the test statistic. It is a z-score. Again, when we're working with proportions, I always get to work with z-scores. And this is the calculation for the test statistic, but we're not going to actually use this formula because note that when we're doing this, we're going to assume the null hypothesis is true. That's always what you start with. The null hypothesis states that P1 and P2 should be equal, which means if you subtract them, you should get 0. So this difference up here, P1 minus P2, should actually equal 0 if P1 equals P2, and that's going to be our null hypothesis that they do. So we're not going to use this version, we're actually going to use this version. Because this version, they just took out this part here, because you said subtracting 0 doesn't change anything. We don't need that part, so we can just use the rest. So this is actually what we use for the test statistic. This formula, where we take the difference of the two sample proportions divided by the square root of, here these going to be the, we'll talk about p hat, or p bar, what that is here in a second, but p bar and q bar, and then the sample size and all that stuff. And this will just give our test statistic. What this is, p bar, q bar, is actually saying, because we're assuming the populations are equal, it actually makes sense to pool the samples when we're using the sample proportion. So actually pool the samples, and that's the pooled value. So this p bar is actually the pooled sample proportion. So we get this by taking the number of successes for both and adding that up and dividing by the number of sampled from both. And that's how we get this p hat. And then q hat would be the proportion of failure. So it would just be the other end of it. Okay, so that's how we get this, the sample test statistic and the, from the pooled sample, all that. And we use that to do either the p-value method or critical method. Remember the p-value method, that once you've got your null and alternative and you've figured out your pooled sample proportion and use that to get your test statistic, then we find the p-value and compare it with the significance level. Remember, if p is small, then if p is low, then all must go. Remember to use the standard normal table, the z-stars table, or technology, which we'll probably just go with technology on this one because it's a lot easier. And then if you're doing two-tailed tests, remember to count both tails, because you calculated by hand. That's a big one here. Remember the two-tailed test, count both tails. If you do the technology, it should do that for you. Reject the null if the p-value is less than the significance level. So remember, you reject if p-value is less than significance level. That's how we determine to reject. And again, use the standard normal table or the z-score table. If you're in critical value method, remember that when you have the two different tails, you have two critical values. Left-tailed, you'll have 1, and so it'll be negative, and right-tailed, you have 1, it'll be positive. So remember, the critical value determine if the test statistic is in the rejection region, and that's when you reject. Again, if you're going to use technology, you're probably not really going to use the critical value method. You can really mostly just look at the p-value method is probably what we're going to use, because that one works great with technology. So we'll find the p-value and compare it to the significance level. Okay, let's do one, and then we can talk about how this works. So we're going to do a problem. So it gives us sample data for independent, so they are independent, they're not connected, simple random samples, so they are simple random samples. So they're just checking off those things we're looking for. From two different populations are provided below. You'll see the number of successes are 11 and 1, and 15 the others. We've got enough successes, and there are the 90 and 50, so there's definitely enough failures as well. So everything requirement-wise is met. Not really a big worry, but you always want to check that. And they tell us to do a left-tailed test. So we're doing a left-tailed test at the 3% significance level. So we're telling us that alpha, significance level, is 3%, and they're telling us to test the alternative hypothesis in this one would be that P1 is less than P2. So remember, that's what a left-tailed test means. We're doing a less than test. The null hypothesis for these two proportions are always going to be P1 is equal to P2. So we assume they're equal. We're checking to see if it's less than. Okay, so first off, to do this, we are going to need to find the p-bar, which is that pooled sample portion. So p-bar, we find that by taking the two sample numbers of successes, so x1 and x2, and adding those up and dividing by the sample sizes, n1 plus n2. So that's how we're going to get the pooled proportion. So x1 is 11, x2 is 15, so we add those on top. On the bottom we have n1 is 90, and n2 is 50, so that's what we got on the bottom. So we get what, 26 over 140? 26 over 140. And that gives us 0.186, or about 18.6%. That's our pooled proportion. Okay, then to calculate our test statistic. So get our test statistic. We're going to use this other formula for z, test statistic right here. So first off, we take the sample proportions, so p hat 1 and p hat 2, which we don't have yet, so we have to find those ourselves. So to get p hat 1, we're going to take our number of successes for 1 over our sample size, so 11 over 90. That's going to give us our p hat 1, so 11 divided by 90, which is 0.12 repeating. And then we're going to do p hat 2 by doing our number of successes for the second sample, second population, over the sample size, so 15 over 50. And you get 0.3. The closer these two numbers are together, the more likely you're not going to reject, right? Because what we're checking is to see if these are different. So you can see 0.12 is smaller than 0.3. But we have to check and see if it's small enough. The hypothesis test is a check to see if this is actually small enough that we can say that the first population has a lower percent than the second one. If these two numbers are really close together, that's when you'll fail to reject, because then they say the populations are close enough to say they're equal. Okay, so we take p hat 1, which is 0.12. I'm going to just round it to 0.12, minus p hat 2, which is 0.3. Let's subtract that on the top. On the bottom, we get the pooled sample, so that's that 0.186. I do 0.186 times the other part. So this is like 18.6%. So the other half would be the 83.4, or 0.834 would be the other. So this is the success, probability of success. This is probability of failure. And then they do that over the first sample size. We'll do it over N1 first. So that's P bar, Q bar. That's why we did, 0.186, 0.834. These should add up to 1 if you do it right. And then on the bottom we have N1, so 90. And then we're going to add that, same thing on the top, 0.186 times 0.834. But now over the sample size of 2, so over 50. That's all under the square root. Okay, that should give us our test statistics. So that's how we calculate z. It's kind of a big mess to calculate z on this one. This is like later when I show you how to use technology, you'll be like, man, I wonder I use technology because this is a pain. I'm going to type this in. I do 0.12 minus 0.3. Here I'm going to show you what calculations are going on so you can see all this. The square root 0.186 times 0.834 divided by 90 plus 0.186 times 0.834. Oh, I missed the decimal. 0.834 divided by 50. Get that all in there, and we get negative 2.59. And again, this is a z-score, so the further it is from 0, the more extreme it is. Negative 2.59, that's pretty extreme, right? That's pretty small, because it's not quite negative 3, but it's getting close to that. So this is a sign that we're probably going to reject. If I'm doing p-value method, p-value method, I would just take this and find the probability of getting that or less. So I would do the inverse norm. So I do that second distribution, inverse norm, or sorry, not inverse. That's my p-value score. I want second distribution. I want norm CDF. My lower value would be like negative 10 to the 99th, something really small. My upper value would be the negative 2.59, and then 0, 1, because we're doing standard normal chart, standard normal table. And that would give you that. So p-value, we do normal CDF. So negative 10 to the 99th, negative 2.59. 0, 1, and that gave me 0.004799. I got to round it a little bit less because this is a really small number, which is less than 0.03 or alpha. So the p-value is less than 0.03, our significance level, and that's enough right there just to show us that yep, we can reject because our p-value is small. Remember, if the p-value is small enough, then you reject, so we reject. So in this case, the numbers were so far apart, 0.12 versus 0.3, they're so far apart. we reject equality and say, no, we're going to have evidence to support the alternative, that the first one is smaller than the second. 0.12 is so small that we can say, yeah, the two populations, the first one has a lot smaller percentage than the second. So we reject the null and support the alternative. If you're going to do this with critical value instead of p-value, so I'll just show you real quick. If you wanted to do critical value, we would use that 3% significance level, alpha. And since this is just a one-tailed test, so we have a one-tail, we just have to figure out what the tail is right here. And we put 3% in this tail. So this is where you'd use inverse norm. I was trying to think for a second there, but no, it's inverse norm for this. Area is 0.03 or 3%. And then that would give us our z-score. Oh, I got a decimal missing. So second distribution, inverse norm, 0.03. And that would give me negative 1.88. That was using the inverse norm, 0.0301. Oops. And that gave me that negative 1.88. So that'd be the critical value. And remember that you always check to see if your test statistic is more extreme. In this case, our test statistic would be negative 2.59, would be all the way down here. It's inside the rejection region. And so since that is less, we would reject. So either way you do it, you'd reject. So yeah, negative 2.59 is less than negative 1.88. So we also reject. So that'd be the way to do it by hand. And again, I'm not going to make you do it by hand. This is not something on test day. Like, oh, you need to know how to do this by hand. All that. But this one, you just can use the technology. But this is the idea of what they're doing. If you're doing this technology, this is what's going on in the background. Is they are pooling all that data together to get your answer, and then creating the test statistic and doing the p-value stuff. If you want to do this with technology, what you're going to use is going to be the 2-prop z-test. Now, you're using 2 because we have 2 populations. That's your big hint. You use 2 when you have 2 populations. And we're doing prop because we're doing proportions. Whenever you have x's and n's like this, you're doing proportions because you're looking at a percentage of the population. We're not looking at means and standard deviations. We're looking at x's and n's, number of successes out of the sample size. So if I want to do 2-prop z-test, I'm going to hit stat tests and go down until I hit 2-prop z-test. And then what you'll have to put in here is you're going to have to put in the x1, which in this one was 11. So I type in 11. You're going to do n1, which in this case was 90. And these are all given to you. So, when you're doing these problems, they'll give you this information. x2, so that's the success rate for the second group, it's 15. So x2 is 15. n2, which is 50. 2 is 50. And then this one is a less than test. So we're doing less than P2. And so I do all that, type it in, hit calculate, and it should just give us the same information we got by hand. It should give us the test statistic, which is negative 2.59. So test 2.59. And the p-value, which I just call p, is 0.004. 7 if you want to have more decimals. And so that shows us right there, again, we get that really small p-value, and we just compare that with that 0.03 alpha, and we reject. And so that's how you could do it with the calculator, and you wouldn't have to do anything more than just type those 4 numbers in and select less than, and you got enough information to do your rejecting on there. It does give you like the p-hat1, p-hat2, so there's lots of information it gives you, but you don't really need that if all you're trying to do is tell if whether to reject. Also, this little p-hat here, it's 0.186, that is the p-bar we're talking about. That is the pooled value. That's what that's showing you. So it actually gives you p-hat1, p-hat2, and it gives you the pooled value, which is kind of an average of these two, basically. So all that information is in there. So again, you can use technology for all the homework and stuff. You don't have to do it by hand. So that's what I'm going to do on the rest of these problems. I am just going to use the technology. I'm not going to worry about trying to do it by hand. So let's try another one. This one's got more of a story, so let's read the story first. So police chief believes that his city has a lower percentage a violent crime than the nearest city of similar size. To show this, he found the following data. So in his city, out of 302 convictions, sampled only 45 were violent crimes. And the neighboring city, out of 2023 convictions, only 231 were violent crimes. We're going to do a hypothesis test at the 0.1 significance level, so that's a 10% significance level. And we're going to treat his city as population 1 and the other city as population 2. So that means that x1, for us in this case, is going to be number of successes for his city, which would be 45, because we're looking for violent crime as the success. Sounds silly to make violent crime a success, but that's what we're looking for. And the sample size for a city would be 302, because that's how many you sample in this city. The successes for city 2 were 231. There were 231 violent crimes. Sample size for city 2 was 2023. And again, he's looking at saying that his city has a lower percentage. So to do this test, he's going to be trying to show that his city is actually less. So we're looking at a P1 is less than P2 situation. So that way, if he has evidence to support his alternative, he can actually show that, yeah, my city has less violent crime. And he can make himself look like a better police chief because he's got less violent crime. Or at least hopefully I'm guessing that's how he's wanting to spin this. So we're going to do a 2 prop Z test. So that's what we're going to do. So 2 prop Z test. Just type in those numbers. So I go stats, tests, 2 prop Z test. So the x1 is 45, n1 is 302, x2 is 231, n2 is 2023. We're doing a less than again because he's trying to show that his city's population has a lower amount of crime. And we'll calculate. And so again, because now we use the calculator, we don't have to figure out all these numbers by ourselves. It just gives us the test statistic, the z-score, which is 1.745 for this one. It gives us the p-value, which for this one is 0.9595. It's a pretty bad p-value. And then it gives you the other values. So you can see here that the first population has a 0.14, and the second one has 0.11. So actually, his sample data doesn't support him at all, right? Because he ended up with more violent crime in his city, 14%, versus their city was only 11%. So that's a bad sign for him. He was looking for the first one to be smaller. So that's why we end up with pretty bad p-value, because p-value, again, we want it to be low. This p-value is much bigger than his 10% significance level, so we failed to reject. In fact, we probably didn't even have to run the hypothesis test. As soon as we saw that his percentage, his percentage is actually higher than their percentage, then the evidence is not supporting him at all. There's no evidence to support his claim. So we failed to reject, can't show lower crime rate in the population one. We did not show that at all. We actually have a higher percentage here than we do over there. So his data is not backing up his claim at all. So he needs to go back to the drawing board or start thinking about things to do to improve this situation because he's not have evidence that supports him at all. But that's a 2 prop Z test. Again, you just need all this, and then we also did a less than P2 because we were looking for a lower percentage. So let's try confidence intervals. So just like we do hypothesis, we can also do confidence intervals for 2 populations. So determine the confidence interval for the difference between 2 population proportions. So instead of looking at, so when we do this, we are looking at the difference between the 2 as going to be the interval we're going to make. So the interval is going to reflect like the subtract the 2 average value, the proportions. Just like always, you can do this by finding the margin of error and then getting the endpoints. But we'll use a calculator, so it'll kind of do all that for us automatically. We assume the populations are equal, which means we expect the difference to be 0. So we use the difference when we subtract to construct our confidence interval. We're expecting to find 0 inside. If we don't find 0 inside, that's when we kind of have an idea that they are not the same. If both of our endpoints are negative or both are positive, that's when you're not going to have 0 in the interval. So there's 3 different results. You can have the lower is negative and the upper is negative. If they're both negative, then 0 is not inside the interval. and you could say the first population is actually less than the second, because when you subtract small minus big, you always get negatives. So that means that it doesn't contain 0, and we reject because they're not equal. If you get negative and positive, then 0 is right in the middle of the interval, and then you can say they are equal, and then fail to reject. You can't really support that they're equal, but you can fail to reject and say we don't have evidence they're not equal. If you get both positive, then that's going to show, again, 0 is not going to be inside the interval, and that's when you say the first function is bigger, because if you subtract and get a positive, then the first one must be bigger all the time. This is the formula for margin of error. We won't really need it because, again, we'll use technology instead of doing it by hand. And then this would be how we typically do it, right? We look at the difference, which we expect to be 0, but then we look at the difference and then add or subtract the margin of error. Now, this won't necessarily be difference 0 because our sample proportions probably won't really match exactly. But this kind of gives us the setup. So let's do it in practice. So, trying to remember if I'm just going to do it in technology. Let's just use the technology instead of trying to do this all by hand, because there's not a real big point in doing this by hand except for just show you once. So this is the information. We're going to do this as a 2 prop z interval instead of a hypothesis. Let's do 2 prop z interval, because that's how we do it when we have 2 proportions. So we have 2 populations, and we're looking at intervals, so we're trying to make a Conf interval. And this is telling us to do an 80% Conf interval, so we would use this for 80%. Okay, so let's go to tests, and if you go down far enough, you'll get to 2 prop z interval. So not hypothesis test, because we're not creating we're not checking a hypothesis. We're creating an interval. So what's the range of values? So x1 would be our 11 that we have up here. N1 is 90. X2 is 15. N2 is 50. The conf level we want to do is 0.8. So calculate this, and that will give us our interval. Pretty straightforward, right? So that's the nice thing about 2 prop z interval. You just put in that data, and then we get the answer. The interval is negative 0.272, negative 0.084. It doesn't give you the margin of error. It doesn't give you the difference between these 2 Conf intervals, or difference between the 2 proportions. But you could always find that, right? So you remember that if you find the middle point between these 2, so add them up, divide by 2, you get the the value for the point estimate. What is the difference between the 2 samples? And if you add these up and divide by 2, you'd find if you subtract these and divide by 2, you'd find how long it is between the 2, and that would give you, and divide by 2 would give you the margin of error. So if you need margin of error, stuff like that, you can, add and divide to get the point estimate, if you needed that for some reason. I don't think this really asked for that, so you really don't need it for this section. And if you subtract divide by 2, you'd get the margin of error. So if you're just curious what the margin of error is or the point estimate would be, you can always take your confidence interval and get those things. But really, we usually are just looking for the Conf interval. So that's all really they want for this. Now that's actually enough information. If you're trying to do a hypothesis test, if you're doing a hypothesis test, you could actually use this to note that there is no 0 in this interval. It does not contain 0. So you would actually be able to reject the null, because you could say, well, 0 is not in there, so I don't think equality fits, and so you'd reject the null. And because these are both negative, you're actually showing that P1 is less than P2, which is actually what we showed in the previous problem up here. We showed that P1 less than P2 with the one more problem. With this 11 and 90 and 15, 50. We showed that at the 3% skewness level. We're actually doing the same thing here, and we're doing it at I think the 10% level, because using the 80% Conf interval, with 10% on both tails. So this is rejecting up to a 10% significance level, whatever. But yeah, that's what we're showing. We're showing rejecting again because it doesn't contain 0. So when you're doing the Conf intervals for this, remember, you're looking to see if it contains 0 or not. Because if it contains 0, you fail to reject. If it doesn't contain 0, then you reject. In this case, because they're both negative, we showed P1 less than P2. That would be what we'd be showing. I'm just going to do one more, and we'll be done. This one just got a little tricky, so I had to point this out to you. So they gave us a sample of random males. It was found that 21 write with their left hands, and 225 do not. And they had a sample of females, and they had 62 write with their left hands, and 44 do not. But notice that typically they give us X1 and N1, right? And X2 and N2, because that's the numbers we need for these problems. But this one, they didn't do that. They did give us, if I'm looking for significance level test claim that rate of left-handedness, I'm looking for left-handedness. So my left hand, that's going to be my X1. That's going to be my X2. So that is given, 21 with left-handed for males and 62 for left-handed for females. I'm going to say population 1 is male, because that's what they gave us first. It doesn't care which one. I don't really care which one's which. It's just picking the first one given to be 1, the second one given to be 2. Oh, this is supposed to be 62, not this one. Sorry. So they gave us 21 left-handed, 62 left-handed, but they didn't give us how many total. They gave us how many right-handed, right? How many are not left-handed. So in this case, we actually have to remember that the sample size is going to be your successes, the numbers that are left-handed, plus your failures, the number that are not. So left plus right in this case. So and actually, to get the sample size, we're actually going to take the left-handed people plus the not left-handed people and add that together. So this case, we have 21 plus 225 would give us 246. The other one, 62 plus 442, that gives us 504. And so that was just using a little bit of thinking there. Now it's really tricky though, because when you're doing these problems, you're already kind of trying to think about everything that's going on and stuff. So when you're doing this homework question, I know this one could throw people. So that's why I wanted to point this one out, that sometimes they can do that, where instead of giving you the number of successes and the total sample size, they can give you the successes and the failures, and you have to add those up to get the total sample size. So in this case, we're going to do a 0.01 significance level. We're going to construct a Conf interval, and we're going to test the claim that left-handedness is less than among females. So we're actually going to do P1 is less than P2 is what we're trying to test. That's our alternative hypothesis for this one. Okay, so if we have a 0.01 significance level and we're doing a one-tailed test, remember that when we do this, we want to have 0.01 in the one tail. So to make a confidence interval, we actually have to put 0.01 in both tails. So we're going to be doing, for confidence level, we're going to be doing 0.98 is going to be our confidence level. That's the whole doubling thing when you're doing a one-tailed test. Okay, so let's use our confidence interval and then we'll test it out. So first off, we're going to do 2 prop z interval. We'll plug this information in. Again, we're going to be doing our confidence level as 98%. So let's do that. So stats, tests, scroll down, 2 prop z interval. I'm going to do my x1 is 21, my n1 is 246, my x2 is 62, my n2 is 504, and then my confidence level is going to be 0.98. That way we get that 1% in both tails. So that would give us our confidence interval. So our confidence interval is negative 0.091 to 0.016. And you'll notice, because one end is negative, the other one's positive, so if we go from negative to positive, it contains 0. So this contains 0, which tells me that I fail to reject. So we're using this confidence interval to fail to reject because we say 0 is a possibility. That means that P1 equals P2 is a possibility. So based on this confidence interval, we're going to fail to reject. So we use the confidence interval to check for whether it's a distinct difference between the two, and we couldn't show that. Now, if we wanted to, you could have done this test with a hypothesis test. So we go to stats, tests, and we do the 2 prop z test. And then we would type in the same value as the 21, the 246, 62, 504, do a less than test, calculate, and give us the p-value, which ends up being 0.06. And we just compare that with their significance level. And you can see that p-value 0.06 is too big. It's not less than the 0.01. So in this case, we would fail to reject again. So you can see how you can check it either way with hypothesis test. So maybe I'll just write that real quick. So just to note, if you do the 2 prop z test, you get the p-value 0.06, which is greater than 0.01, alpha significance level. So then we fail to reject as well. So it fails to reject either way. The only way we would have been able to reject this if they wanted like a 10% level test instead of a 1% level test, because this was like very great data. So that's the idea. You can build the confidence interval. Again, a lot of the math is happening in the background, right? Because you're making the calculator do all the number crunching. But you do have to make sure you have the right data fed into it. And it's really easy for people to type in 21, 225, 64, 242, because they're not being very careful with that. Remember, we have the number of successes and the number total, not the number of successes and number of failures, which is this. So these ones, again, these are both failures, and that's why we couldn't use them, because we wanted sample size, not failure size, when we're doing these calculations. So this idea, what we're doing here, Chapter 9 is going to be all about doing hypothesis tests and confidence intervals with more than one population. That's going to be the big theme for Chapter 9. So you'll see a lot of this where I'm going to show you how to do it a little bit by hand, and then we'll basically pull out the calculator and see that the calculator will do most of this for you. The idea is recognize the situation. So here we should note in this section, the reason why we know we're doing either the 2 prop z interval or 2 prop z test is because we have 2 populations, and we have a success rate and a sample size for both populations. We're looking at x's and n's. We're not looking at those means and the standard deviations. That's when we're looking at different stuff. We're looking at proportions. We're looking at percentages. So those p's and the x over n's, that's what tells us I'm going to be working the props, proportions, and those are always z-scores. So that's it for 9.1. So we're done with this section. And we have 2 more sections of 9 to go through. So I'll see you on the next time.